has no shame. I mean, it's sad. It's very sad. Mm-hmm. No one loves him. Can you tell how no one loves him? Yeah. Ozzy, do you like her a little bit? Miss her next year. Yeah, you're gonna have to come back and visit. Without her. Do the tail. And my mother hates dogs. And her dog was probably all the time. Not well. He really can't help himself. It's ridiculous.
So I'm waiting for the state release December 15th.
Yeah, hold on.
Where's my oh,
yeah, the last one that Cole had that we were waiting on to come to March. Done.
Go ahead.
March 15th. Yeah, good. All the other not great. Look. Who is that one? Hi, Tony. You got a random text from one of my past students last night. I don't think you met her, but she loves her last year was the year we did chemistry, so you missed her. But no, you were here for chemistry. Yeah, Kai. Remember Kai?
Yeah.
Okay, so I got a text from Kai and blew my mind because she said that you're the only one that was here for chemistry through junior. Anyway, she wrote that some Arizona State Unity Leadership Company or something like that. And now she texted me to tell me if she's going to Gwinnett Tech for geoscience. That's taking back to our electronic plates and decided she was going to go learn about something she actually was interested in rather than doing what she thought she could. Which I thought was very interesting. I was like, wow, all right. I screen captured it and sent it to Cole, and I was like, "We're not doing that with this stuff." Cole was like, "What? What's that?" Oh, yeah, because so if it doesn't change the size of a force, what are the other things? You're not changing the size. I think when you lift down, look at the massive. You pull down and that plant it's gonna change the direction, right? So if you need to change the direction of something, that's where they kind of really can do like conveyor belts and all those sorts of things with direction. Yeah. Like that. What?
That's exactly what we needed, right?
Yeah, he's going to suffer.
Anyways.
There's a Instagram going around with edit that one. And I took his picture that this lady talking about doctors being murder hounds.
I call them German engineers, hunting meetings. When they learn that they can hunt rabbits, that smoking, they're. I love murder hounds.
Hounds. Murder hounds. Yeah, this was my. Come on, and he had a tongue out, teeth out, two teeth, like.
Kind of like the people who get thrown out in the apartments and
Yeah.
like can't have vicious creatures and then just show them an adorable,
Yeah.
most vicious creature picture they have.
Yeah, little tiny dog. Well, chihuahuas are like, woo.
Does everyone need to turn one in?
One per team.
Okay.
Turn it in today before you leave, and we'll be good. Get another drink. Wow, that's good.
Stable as I. Make it taller at the top. And it was actually, it's so tall. You did jump down. My dad, every time he wants to put it in action, says, you're a no. What the heck? We must be black.
Yeah.
Yes, it's posted. What's happening in our creation? What's your name? Gertrude. Wait. How about we just name it? Oh, it is 1 hour. What? 1 hour? Yeah, I know. Hey, yo! What are you talking about? It's moving. Wait to go. Look, that was all right there. That was all right. Thank you saying that.
They're showing that to everybody now? Okay,
I get.
this is mine.
Banana don't make sense. Yeah. It's great. Next school.
Y'all are crazy, I love it.
Oh, no. The annual control will be on before we can say exclusion is already right.
So y'all, I found what might be good news depending on who you are. So I figured I would pull up this video to show you.
Oh, I've seen this. Oh, yeah.
Looks like we may get some serious snow this year.
In this video, I'm going to tell you that on behalf of the store, I would get home. decade.
Give it.
Showing you how much vegetation gets each year. So go ahead and pick out your state and around where you're sitting at, and let's start with these seeds, the least snow. In fact, this first zone doesn't usually see.
Oh, you okay? All right, cool.
Anywhere from a straight up snow all the way up to 3 inches here. This is really places like Atlanta, Georgia, Austin, Texas, and Vegas. If you go just a little bit farther north, you'll find yourself in an area that sees anywhere from 3 to 6 inches of snow per year. And that's going to be all in Charlotte, North Carolina, Little Rock, Arkansas, and Portland, Oregon. We also have places like Nashville, Tennessee, Oklahoma City, and Seattle getting in on anywhere from 6 to 12 inches of snow each year. And just a little bit farther north from that.
Oh, now a commercial.
Concealed carry, you're gonna need a tackle.
Yeah, all right.
I'm gonna tell you.
America. All right. There you go.
When do ads ever work?
Oh, no, man.
Have a much bigger zone where we can see anywhere from 12 to 24 inches of snow in a typical year. This is the zone that I live in. St. Louis is in this one, Cincinnati, and Wichita, Kansas. And then everywhere north of these zones pretty much measures in feet. We usually get 2 to 3 feet in Philly, Des Moines, and Bismarck. And then everywhere north of that, anything goes above 4 feet. 4 to 5, 6, 7 feet, you name it, especially in places like Buffalo and around Denver. But of course, like I've been saying, what you see on this map is probably not exactly how much snow you're going to see this year, because this map shows you a typical year, and our upcoming winter season is not looking very typical. We know this because for the first time in years, we're going to be entering our winter season in a full-blown El Nino. The waters in the Pacific Ocean are much warmer than usual, and this significantly impacts the overall weather patterns here in the U.S. Usually, things get a bit warmer in the north-central U.S., and we get this amplified storm track across the south, making it cooler and wetter. But even this is what happens during an average or typical El Nino. And no 2 El Ninos are exactly the same. For example, the last time we were in a strong El Nino pattern, we got a historic blizzard here in the States in January of 2016. But there are several examples of El Nino winters in the U.S. with no notable snowstorms, or even a few that feature below average winter activity overall. The current state of our El Nino is moderate, but forecast models continue to promote the idea that the waters are going to continue to warm, and we're going to make a run at having a strong El Nino by December or January. This means that the effects of a typical El Nino could be somewhat exaggerated right around the time we start to experience our most intense winter weather here in the States. And it's not just El Nino that we have to consider when making our winter snowfall forecast. Another thing I've been hooting and hollering about all fall are the very warm temperatures in the Atlantic Ocean, which actually have nothing to do with El Nino. I mean, it's currently early November, and we are still monitoring potential tropical systems out here in the Caribbean. This tells me that there's going to be a lot of extra energy that usually isn't there, just floating around down here as we go deeper into winter. And remember, we're going to have that very amplified jet stream crossing the southern U.S. around this time. So any storm that gets going down here is very easily going to be able to absorb that extra energy, say, in the Gulf of Mexico, and then use it to strengthen significantly. These storms are very likely going to bring severe weather to the southeast and potentially pull down enough cold air to cause snowstorms. Now, of course, none of this is set in stone, but it does align with the bracket that I made months ago that featured my call for who's going to see the biggest snowstorm this year, or who's going to see the Big Daddy snowstorm. As you can see, even back then, I saw the potential for this southern storm to phase with or interact with some northern energy that contained cooler air. But now that we are actually close to winter and we have a lot more valuable data, in order to make this prediction even more accurate, I would actually move these zones down a little bit farther to the south. But the important thing to remember is that one Big Daddy snowstorm is not going to make or break your yearly snowfall. And that's really what this video is about. One year you can see a big snowstorm and then still have below average snow. Or you can see a bunch of tiny snow showers that add up to above average snow by the end of the year. So let's stop all the jibber jabber and get right to the point. Okay, why are we here? We want to know how much snow we're actually going to get this year. Well, considering everything we've talked about so far in this video, I think I have a pretty good idea. So here's my big shiny brand new map showing where I think we're going to see less snow than average this year. I really think the warmer El Nino induced temperatures are going to negatively impact the total amount of snow we see up north this year. So much so, I've added another zone, a dark yellow zone, where I think we're going to see way less than snow. And first of all, energy, Atlantic, jet stream storm track. I think we have a really good chance of seeing above average snow in the south this year. I'm not really confident enough to add a way above average zone, but it was really close over in the Appalachian region and over close to their land. So go ahead and take another look at this map showing the average snowfall in your area and keep the range in your mind, and then compare it with my forecast map. Are you in the yellow, then reduce that range by 15 to 20%. Are you in the dark yellow, then you might as well take off 30 to 40%. But if you are in the blue, you can add anywhere from 15 to 25% to your average snow range, and you've got how much total snow I think you're going to see this winter. And of course, as always, I could be wrong, and I want you to hold me accountable if that's the case. Get out there and measure your snow, okay? Keep track, and please send me those reports when you can, because as we approach peak snow season, we are preparing to go live during every single big snowstorm right here on YouTube. We're going to have storm chasers on the ground. We're going to be in contact with local road crews and everything you could possibly need to stay up to date whenever that next big snow or ice storm hits. But a very big part of our snow coverage includes you. That's why I have developed the Yolometer 2.0. This thing is the most capable snow measuring device on the market. It's big, it's bright, it's beautiful, so it pops whenever you take those snow measurement photos. It's very pleasing to the eye and easy to read, and it even gets the kids into measuring snow. And it allows us to tell the story of every snowstorm by creating a huge database of accurate snow reports. It also just so happens to be how we raise money to invest in storm chasers, scientific probes, and other special equipment for our severe weather live coverage in the spring. So if you'd like to help out and join in on the fun this winter, go ahead and go to shopryanhall.com right now to get yourself a Yolometer 2.0. Just like last year, we're going to do a bunch of fun competitions with the Yolometers during our live coverage. Just as long as you send in a snow measurement photo during one of our snow streams, you're going to be entered to win $1,000 at the end of that stream. That's right, I'm going to be giving you $1,000 for measuring the snow. And this year, instead of just giving one person $1,000 at the end of the stream, we're going to give two people $1,000. And guys, there could be like 10 to 20 snowstorms this year, so the odds are in your favor. All you got to do is click that link at the very top of the description and get you a Yolometer over on shopryanhall.com. In fact, if you get one within a week of me posting this video and you use the discount code I am ready for snow, you're going to get 20% off the Yolometer. And shipping is only $2. So this is a deal you shouldn't pass up on. I'm excited for our coverage this year, and I'm so happy that so many of you want to be involved. And I can't thank you enough for giving myself and the team here literally the best job in the world. So see the next one. Goodbye.
You think he's right? You think they're gonna get more snow? I think so. Hi, Queen Latifah. What you doing?
All we know is how hot it was throughout the entirety of fall, but.
Oh, yeah? It was very, very warm, unseasonably warm, unseasonably late this year. So that's kind of, that's odd. So that's what he's saying, is combining all that with the, you know, the routine El Nino stuff, and then it's like, okay, we see an interesting pattern. We might actually. Do you guys like when it snows? I love it.
Yeah, I love snow.
I like
snow, but I don't like it when it's slush.
Oh yeah, that's worse.
It's like impossible.
Yeah. I do, I like the snow. I think it's cool because I don't see it very much, you know. There's two different patterns, El Nino and La Nina. So one is the boy and the girl, and there's a whole like I can't remember the exact specifics. Then there are the specifics and the patterns between El Nino and La Nina. I can't remember the moment. My brain is not putting it to my head. Yeah, no, but it's a pattern. It's a weather pattern. It's a repeating thing. It's a pattern. But you know what? They're different, and it has to do with like the way the warmth in the Pacific. Hang on, I'll tell you.
Oh, it's the jet stream.
Yeah, so it's something to do.
Jet stream moves like north and La Nina and down.
So La Nina is colder Pacific waters and precipitation drops, and El Nino is warmer Pacific waters and precipitation increases. So that's what, yeah. So El Nino is a warm phase, La Nina is a cold phase. And they're cyclical, they're relatively cyclical and somewhat predictable at least, but that combination of all those warmer Pacific waters bringing in more precipitation, and then the fact that there's still warm pockets in the Atlantic right now that are not usually there at this point, that's pretty crazy, like, not normal, so maybe we'll get lucky and we'll get some snow. So you guys know our rules for the snow are basically, if Forsyth is closed, we're closed. If your county is closed, you're closed. And if it doesn't look like you can get here for whatever reason, stay home. It's fun. We can do a class online. You can get to it whenever you want. We don't get snow often enough for us to force ourselves to continue through it. You guys should absolutely be out enjoying it. I mean, shoot. We need more snow. So, has anybody been out at night and looked for the meteor shower?
What?
Huh? Y'all like, I go out at night. Yeah. No, there's a meteor shower in November. It's an annual thing. It's the Leonids. So, it's supposed to be pretty good for the next like week or so. Thursday night, I left my choir rehearsal, went back from inside the church to the choir room to drop off my music, and me and two of my friends were walking out of the choir room back towards the parking lot, and there was this greenish light, really bright, that went like right through the sky, and we all looked up. My friend is like, what was that? Was that a meteor? And I was like, I think it was. So I mean, it's pretty cool. I think it was 1830 something was the most visible event. There were just several things clicked together perfectly well, and it was very shocking. Like certain people in North America, at least, there were certain people who thought it was a sign of the second coming. Like people were pulling out what were they, St. John the Divine and a couple other things, and they're like, oh my gosh, the stars will fall, Jesus is coming. Like everybody got ready. Like it was like craziness, right? There were stars, lots of shooting stars, and so there were obviously people being prophetic about it, and nobody showed up, but hey. And yeah, it was this is the same meteor shower, and it was actually, the reason I'm mentioning it is because that guy with the weather he's talking about like crowdsourcing data, right? Well, that particular meteor shower in I think it was mid 1830s, that was one of the first examples of crowdsourcing data. So there was a guy at Yale at the time, and meteorologists didn't have the best understanding of shooting stars, but they were curious about it. So he basically crowdsourced data from all over North America. What had people seen? When had they seen it? And, used his telescope and whatnot, and found that they seemed to be kind of originating from, at least from where he could tell, from the constellation Leo, which is why there are Leonids. And it's an annual thing every November, but they're pretty good right now. If I saw one and I wasn't even looking, it just popped up at me, then if you go looking, you might find one. Pretty cool. All right, so don't show up next week, right? Everybody knows that. Don't show up next week. I love you, but I'm not letting you in. You can go home. Next week is Thanksgiving. Yes. Yeah, you can walk home. That's right. All right, so work power machines continued. All our little rats today are going to be in little Victorian factories, like poor little workhouse rats. Oh, poor things. All right, so mechanical advantage and efficiency. Let me make sure I have extra paper out, because you guys in the back might not have any over there. You can want one probably. Sure. All right, so here's paper in case anybody. Ooh, sorry, paper. All right. So, all right, so the number of times the machine increases an input force it's what, Caitlin? It's mechanical advantage. Okay, now we're going to talk about both mechanical advantage and efficiency. So mechanical advantage is going to be given as it's a number. There are no units, and you'll see that when we get to it. And that's because the units actually cancel out. And you're really talking about the number of times the machine has increased your input force. So when it comes to mechanical advantage, we have basically two categories. All right, Lucas, what have we got?
Actual mechanical advantage?
Yep. And what's the other?
Right here.
Liam? Ideal mechanical advantage. All right. So you have your actual and your ideal. All right, now, your ideal is what you can calculate based on the information you have. Yes, Drew?
Actual is without friction.
Yes, that's what I'm getting at. Right, so actual is your with your friction. Your ideal is without it. So what does ideal mean, Bailey?
Basically what we want, but we can't ever have.
What you want, but you can't ever have.
Possibly have if we're like a very good vacuum.
Yeah,
Even
yeah.
vacuums would still have some friction.
Yeah, you'd have to be in like a vacuum in space, which means you wouldn't be alive. But that way you'd have no friction or less friction. Yeah,
Some of it.
there you go. There you go. So yeah, so it's friction that is gonna mess up everything we do in physics. It's gonna always get in the way and always has to be considered. So when you are calculating based on input that involves force, most of the time what you're gonna be calculating is your ideal mechanical advantage. But sometimes you actually are calculating the actual because you have, depends on what data you're given and what data you need, basically, right? All right, so friction's always present. So your mechanical advantage is always going to be less. Yes, Jordan.
So
Mhm.
it says that it's lesson 13, but on the next page.
Oh, it's
okay, hold on,
14.
Look, it says 14.
Yeah, that's a misprint.
Also,
So
a lot of the dates are wrong.
yeah, that was one of the ones where I was like, it's going to be, there's some screwiness in there. So yeah, I think it got, actually, the whole thing got copied over wrong, the whole thing. But somebody already sent me that one, so we caught it. But yes, we caught it. Very good. Yep, I'll make sure that it's correct in your email, so double check. All right, so how do we calculate it? So Yusuf, what do I want for this first one? What's always easier to calculate of the two?
I do the same.
Yeah, your IMA, right? And it's because you are dealing only on your locations and your forces and your distance over which they act. So the percentage of work input that becomes output, Colin, what's that? That's your efficiency. Okay, now it's a percentage. So what does that mean? What's a percentage? What's percent mean? Caitlin. Per 100. All right, so here's where you have to think for a minute. We said a second ago that your mechanical advantage is a ratio of your output and your input, right? Okay, and then your efficiency is a percentage. So they are not going to be the same number necessarily. So think about a fraction for a minute. Let's take the fraction 3/4. All right. So if we go back and look at, where am I looking? Okay, output force to input force. And then we're also told here that because friction's always present, your actual mechanical advantage is always going to be less than 1. So we're also talking about it being a ratio. A ratio is essentially a fraction, right? Okay, so if I said your ratio was 3/4, what would it be as a fraction? 3/4. Okay, good. All right. So 3/4 is your fraction, right? And so that would be your output over your input, and it's less than 1, right? And it's less than 1 because your friction's always present. All right. Now, because there's always some friction, this is what we're saying. If we're thinking about a fraction, then like 3/4, for example, in this case, that means that your efficiency is always going to be less than what?
100%.
Less than 100%, or yeah, less than, it's always going to be less than your whole number, because fractions are not a whole number unless they're, improper, right? So keep fractions in mind, because sometimes fractions, sometimes thinking about money, this is why sometimes thinking about money is helpful when you're dealing with fractions and percents in particular, because we're more familiar with coins, right? And coinage. So what's 3/4 as a percent? Does anybody know straight off the top of their head? Okay, Asher.
25%. That's our son.
75%, which is, if we were talking about coins, what is it then? Coins.
Oh.
How much cents is it, Drew?
75 cents.
75 cents. Okay. So, right. So sometimes that helps. Just keep in mind, fractions I don't know how much math, everybody comes in at a different level of math, which is fine. Like in public school, they make you take certain math before you take certain science. Yeah, but I'm saying like, I don't do that because everybody's math and science are at different levels in homeschool and that's totally fine. So just need to make sure everybody knows that ratios are fractions. Fractions can be made into percents. How do you make a fraction into a percent? Yusuf.
You have to multiply the base and take it from 100.
So you take the top number and what do you do?
You take the top number and times it by 100. So what I do is I take the top number, I put it over 1 because it's decimal,
Yeah.
and then I just times it times 100 over 1.
Yeah, so if you took 3/4 and you wanted to make it into a percent, you would divide 4 into 3, which you could do by long division if you wanted, and you would get that 0.75. So to make it into a percent, you just multiply it by 100, right? Move your decimal twice and you get 75%. Yeah,
Hey Siri, what?
that's how you do it. Yeah. Yeah, that's my kid. All right, let's give this one a shot. So here's your AMA for a particular machine here. It's a force of 200 newtons is applied to whatever this machine is in order to lift a 1,000 Newton load. So what's the mechanical advantage of the machine? So you have to read in input and output based on this. So what's our input going to be? 200 newtons. That's what we have to put in order to lift 100 Newton load. So that means our output force is, 1,000 Newton load. So our output force is 1,000 because that's what we have to lift. Okay, so take a second.
Why are the rats with
Oh no, they're working.
They're looking things, there are.
Maybe they're
They're busy.
making something that's supposed to lift something.
They could be. I don't know. All right, so who's got it? Anybody got it? All right, Xander, what you get? 5. Okay, so F sub O would be what? What do you suppose F sub O is, Bailey?
That is force output.
Yes.
The FI force input.
Right, so F sub O is output force. F sub I is input force, okay? So you're gonna take your output force, you're gonna divide your input force into it. So in this case, we had 1,000 newtons, 200 newtons, and we're gonna come up with 5. Because these newtons cancel, boom, 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 they're gone. You've got no units for mechanical advantage. No units, it's just gonna be 5. Because remember, it's basically how many times the machine increases the force that you put in. So it basically increased it 5 times. All right, here's a different one. The efficiency of a machine is 40% and it does 120 joules of work. Ooh, I'll give you a minute. And there's your efficiency up there. Work output divided by work input times 100. Anybody thinks they have it? Want to give it a shot? Bailey wants to give it a shot?
48.
48? You want to give it a shot? 2 of you got 48? What'd you get back there? 0.3. Liam, what'd you get?
48.
48, 48, and 0.3. Well, we got some variety here. So let's see where are we going. All right, so the first thing we're gonna do, W sub O, W sub I, work output, work input times 100. All right, but we know the efficiency. All right, so when you're in a situation like this, make this guy into a fraction too, 100 over 1, right? Just much easier to do that. And then we're going to have to swap the positions of these dudes because we want this, right? We're looking for the W sub I. So what do we end up with? 300. Oh, yes.
Shouldn't the
Did I mess one up?
12,000 since you don't find bracket?
And-
it should.
oh, yeah, we're missing it. Are we missing a 0?
Yeah.
Oh, we are missing a 0. Good. 0, no, 12.
Yeah.
Yep, we are missing a 0. Good call. Oh, let me make a note to catch that. That's what happens when you're tired and typing up slides. Good catch. Good catch. Make sure I fix that one later. Okay, so yes. All right, now let's think of simple machines. All right, now I told the other class, I'll tell you guys too. So I got two really cool Rube Goldberg machines at the end of this slideshow for you to have some inspiration. I'm going to try and get your Q4 team stuff to you, at least your groups, before you leave for Christmas break. Okay, so that's like within the next couple lessons.
Q14.
Q4. Did I say 14? My brain is, sorry, I'm kind of
I was like,
right now.
there are that many quarters.
No, it's gonna be a day like that. Yep. Okay. So yeah, Q4. I'm gonna try and get that together before you leave for Christmas break, so you'll know who your teams are. And one thing I'm gonna do this time that I didn't get the chance to do last time, because last time we did this course, COVID hit. That was 2019 to 2022, 2020. Sorry, it was just a dead year. It was really bad. But anyway, I'm going to create for you guys a like a resource library for equipment you can check out. So you'll be able to check out like the ramps, remember when we had the Hot Wheels ramps? Like you'll be able to check out the ramps and other things, pulleys, stuff like that, that you can actually check out and use. And then, you know, I'm gonna make sure you guys have real specific stuff. So lots of simple machines. Yes.
Checkout as in like to look at it?
No, checkout is in like borrow it for the course of your machine building and running, and then return it, hopefully not destroyed, because that would be bad. Yes. So yeah, that's the idea. So there will be some things.
Like a library?
Yeah, like a library, like a resource library for actual equipment, because there's a lot of simple machines that I have that you can use.
So we can bring things from home as well.
Yeah, you're allowed to bring found items, and there's a limit on what you're allowed to buy. So
I want to feel some of Alex's Hot Wheels cars stuff.
there you go.
Because he has a motor that pushes something.
Oh, that's cool. Okay, cool. All right, so our types of simple machines. All right, so I have Wilhelm out over here for a reason. But I'm gonna show you a couple different simple machines that are in your body. That's why he's still out this week. So we have our 6 main types. We got lever, wheel and axle, incline plane, wedge, screw, and pulley. All right, now levers. Here's the deal with levers. You've got, I'll show you real quick before we do that. Well, incline planes and I'll say it later. Never mind. Like I said, my brain's a little dead today. All right. So levers are your bar that move around your fixed point, and the fixed point we call what? Ridley? Fulcrum. All right. So your fixed point is your fulcrum. All right. And then last week, I think you had some of this verbiage was a little different in your lab, but your distance between your input force and your fulcrum is what, James? Yeah, input distance. Sometimes you'll see it as input arm, and sometimes you'll see it as effort arm. That's what I think your lab last week said effort arm. Did it use the word effort? Did it say input arm? Okay. Sometimes you'll see it as effort arm. And then the other one, which is the distance between your output and your fulcrum, is Chloe. That's your output arm, or your, yeah. And that's also, do you know what the other word for that is? If you don't see it, do you know what it might be?
Load arm?
Load, right. Okay. So you may see effort as what you're putting in and load as what's coming out, the output. So if you see effort or load, it's just input and output. It's the same thing. All right, so types of levers. You got your first class levers. All right, these are the ones that you think of as teeter-totters. These are easy to think of, right? All right, so Liam, your fulcrum is located between your input and your output force. All right, so pliers are a great example. There's your fulcrum, right? Here's your load. Here's your effort. And if you look, you'll notice that there's a long arm. Your effort arm or your input arm is long. Okay, that's going to increase your force down here, right? So we've increased the distance on one side, it's going to increase the force on the other. All right, so how about this one, Yusuf?
The output force?
Yeah, the second class levers, yes, your output force is going to be located between your input force and your fulcrum. All right, so if you look at,
He's not using the wheelbarrow one.
No, he's just looking at it. He's going to load it up and then he's going to use it. Okay, so wheelbarrow is your best example here. You got your pivot on one end. All right. Your load is what you're lifting. This is your output. It's in the middle. And then your effort's on the other. James, did you have?
For the first class lever, is it teeter-totter first class or a third class lever?
So it would be should be a first, because say you're here, you're the effort, and you're lifting this person over here. If you're putting the effort down and they're being moved over here, going up in this case, that should be first, wouldn't it?
You're pushing and you're lifting yourself up.
You're lifting, well, the problem with the teeter-totter is there's force on both ends. So it's kind of harder to, it depends on who's doing the pushing, right? But if you are pushing yourself up and they're going down, you've still got your fulcrum in the middle. So that makes it a first class. And then when they push up, you go down. So it's still, but it's like switching which side is effort and input constantly, right? Effort and load.
It would be a third class size.
If you were what?
If you were on it by yourself.
Oh, yeah, well, yeah, that wouldn't be doing you much good, would it? It would be really boring. I've sat on one by myself before as a kid, like hoping someone would join me. Really boring. All right, so the next one would be Caitlin. What about this third class lever? Yeah, okay, so you've got your input force located between your fulcrum and your output force. So a shovel is a really good, clear example. So how's this work? Your pivot's down here, but your effort or your input is in the middle, and your load is on the other end. So in this case, if you look at him, so the pivot is actually in his hand. That's the end back here, right? This is where your fulcrum is. And then what you're lifting is at the far end, but your effort's being put in the middle. So if you look at it this way, here's your load or your output, here's your input force, and then your pivot is back here. Yes.
Do you actually see the big boss rat who went to the factory?
No, but I bet he's scary. Because if these are like truly Victorian rats, he's probably the only one that actually eats every day, you know, and the others are probably all starving and full of disease. Yeah.
So if you're sitting on a seesaw and you have someone who's the same weight as you and you guys are balanced, is it still a first class lever?
If you have, that's a good question. Okay, so Yusuf said if you're on a seesaw and there is somebody on the other side who is exactly the same mass as you and you're perfectly balanced, are you still a first class lever?
Depends who's doing the question.
Well, if you're both just balanced, what do you guys think? Because that's a really good question. I'm not,
Yeah.
I would say it's, at that point, it's not a lever because there's no force being put in. Or the force is balanced, or fourth, you just gonna make up one.
Yeah.
I mean, it is technically, there's still a pivot. Yeah, but I mean, the fulcrum is there, but it's not moving about the pivot. So that's interesting. If we defined a lever right here as a rigid bar that's free, yeah,
Except it just has equal force.
I think that's the case. Yeah, because if we're defining it as a rigid bar that's free to move around a fixed point, then it would be free to move around a fixed point, but we would have balanced force. Yeah. So basically it would be a first class lever, but it's not being used. There's no, it's everything's canceling. Your forces are all canceling. All right, so here's one for you. We're doing IMA here. So input distance over output distance. This is why your IMAs are going to, your ideal stuff is going to have distance because there's no force involved. So we're not actually calculating how much force is used. So friction isn't a thing here. We're just talking distance. So construction worker uses a board and a log as a lever to lift a heavy rock. So you can picture that, right? You got your rock and you got your board. Okay, to lift a heavy rock, if the input arm is 3 meters long and the output arm is 3/4 of a meter long, what's the mechanical advantage of the lever? IMA is input divided by output. All right, Colin, do you have one? 4, he says. All right, so L sub I is going to be lever input, right? And L sub O is going to be lever output. So we have 3 divided by 0.75, and that's going to give us 4, right? So if you had 4 stacks, each containing 3/4, you'd have $4. I mean, $3, sorry, right? Right. All right, so then we have wheel and axles. All right, now I will tell you that when you start getting into wheel and axles, and then when you get into screws and stuff, Wheel and axles aren't too difficult to do the calculations for, but you have to pay attention to whether you're looking at radius or diameter. Screws are like kooky, and we're not gonna do calculations for screws. So your wheel and axle consist of 2 discs or cylinders, each with a different radius. So to calculate your IMA for a wheel and axle, you need to divide the radius or diameter where what, Ridley?
Input force.
Where the input force is exerted by the radius or diameter where, what's the rest of it, Ridley? Where your output force goes. Okay, so this is what I mean by you have to pay attention. If you are comparing radius to radius and diameter to diameter.
From the contentauthority.com.
Excuse me?
Radius is used to
Yo,
describe the distance from the
Alexa.
center.
Stop. Dang on, she's psycho. Okay. Ratio of radius to radius and your ratio of diameter to diameter. How do the ratios compare? If you have radius for the same set of wheel and axle, diameter to diameter, how do those ratios compare using? They're the same, right? Because the diameter is just twice the radius, and it's twice the radius in both your big, your outer and your inner wheel or cylinder. So basically, you have to do either, it's apples to apples or oranges to oranges. You can't do radius in one and diameter in another without converting one or the other to the other unit. So if you've got diameter for one and radius for another, you can double the radius in the second one, or you can divide the diameter of the first one in half. But you have to work with the same units. Does that make the slightest bit of sense? Clear as mud? All right. So here's one for you with that. What is the mechanical advantage of a wheel and axle where the wheel has a diameter of 10 centimeters and the axle has a diameter of 2.5 centimeters? Okay, Lucas? 4, he says. All right, so you have your wheel radius divided by your axle radius. And that could say W sub D and A sub D as well, right? Instead of W sub R, right? Because that's radius. So you have your, that should say 10. Yeah, sorry, it's a typo from earlier. I actually changed that one earlier today because I had the whole thing different. I had all the numbers different and I didn't change them, but yeah, you're right there. Oh, hello. So what I was meaning to do with that tile, there it is. So what if we change this? Okay. What if instead it read, what's the mechanical advantage of a wheel and axle where the wheel has a radius of 5 centimeters and the axle has a diameter of 2.5 centimeters? Would it change your answer?
Yeah.
Would it?
No.
No, yes, no, yes. If I said, what's the mechanical advantage of a wheel and axle where the wheel has a radius of 5 centimeters and the axle has a diameter of 2.5 centimeters?
It's still before.
You just convert it.
Yeah, why would it still be 4?
Because 5 times 2 is 10.
Yeah, because diameter is twice radius, right? Radius is half diameter. So if this had the word radius in it instead of diameter, we just have to get them the same. So yeah, we did that. All right. Inclined planes. Okay, inclined planes are your slanted surfaces along which a force moves an object to a different elevation. So here's a ladder. A ladder is a type of modified inclined plane because it has little steps in it, but it's essentially an inclined plane. So the ideal mechanical advantage of an inclined plane is what? What? Okay, Liam, give me this one. What is it?
Is the distance along the inclined plane divided by its change in height?
Yes. Okay. Distance along the plane. Up. No. What?
There's supposed to cancel, but
I know, but why did it throw that at me?
I have a question.
Yeah.
So you said the ladders are type of inclined plane. Is it still true that the ladder's straight up and down?
So when you take a ladder and you put it straight up and down straight up against a wall, is it still an inclined plane?
No.
No, it's not. Just like a ruler, if I laid it on a table, it's not an inclined plane. But if I put one end of it on a book, now it is. Ta-da! It just becomes whatever you're using it for, essentially. Now, when it says here, the distance along the inclined plane, you have to remember that that might not be the same as the distance from the one end to the other end. So if your inclined plane is shaped like this, you're not measuring here to here. You're measuring this distance along the plane. Okay. Did you have a question, Colin, or you were gonna?
I was about to say the exact opposite of that.
Oh, what were you gonna say?
You're not measuring like the length of the actual board, you're measuring like here.
Ah, yes, along the plane. So you want along the plane. All right, so the ideal mechanical advantage of an inclined plane is the distance along the plane divided by its change in height. Change in height. Okay, for most of what you're going to be doing, you're going to be starting at probably 0. So if you have, you know, your final height minus your initial height, you're just going to, your final height's the, you know, minus 0. But if you are involved in some calculations where you're maybe changing altitude or height through various inclined planes, or maybe you're moving the angle of your plane, that's when your 0 may not be 0 anymore. Okay, so 50 newtons are required to lift a 500 Newton cart to a height of 1 meter using a 10 meter long ramp. So what's the mechanical advantage of the ramp? Yeah.
1 or 10. Sorry.
1, 10. Ooh, he's fast. Anybody else have a different answer?
No, I just know there were just 3 other mouses.
Oh yeah, they're somebody working back here. I don't.
No, like the computer mouse is like the.
Oh, did it? Okay. I don't know. Our internet went out already once today. So, all right. So here's what you're doing. Yes.
That guy looks like he owns a cat.
He might. He's sliding into work. He didn't have to do stairs. So here's your ramp sub L, right? And your ramp sub H. So your ramp length, your ramp height, and there's going to be one way to do it, and another way to do it would be this way. So you've got lots of information in this problem. So if you're using the ramp length, it's a 10 meter ramp, and you moved something by 1 meter. So 10 is your mechanical advantage. Remember, no units, because your meters are going to cross out. Another way to do it is to say, well, it required 500 newtons to move, required 50 newtons to move a 500 Newton cart. There's another way to do it.
Why did you get the 50 Newton? Oh, it's because it's right there.
Yeah, but it's not in numbers, see, so it doesn't stick out. So you have to be careful how you read
I
the
thought
whole
that,
thing.
I read that was like 50 as like a name or something.
Yeah. 50 newtons are required to lift. So in this case, this is basically your output force and your input force, right? So you also have 10. So you can get the information that way, both ways. All right, now wedges and screws. All right, wedges and screws, if we're being technical here, are really what? Liam, what are they?
2 inclined planes, so forth.
That's your wedge. Yep, your wedge is 2 inclined planes, and your screw is actually going to be an inclined plane as well.
It's just very long.
Yeah, so really they're modifications on the same thing. It's the same process, same tool, basically. It's just being used slightly differently. So your wedge and your 2 inclined planes slope towards each other. Now your thin wedge has greater mechanical advantage than your thick wedge. So I want you to think about like working in the kitchen, and you've got a very, very, very sharp blade. So that means it's very, very, very thin, as opposed to not quite as sharp a blade, which is much wider. Obviously, that thin one is going to have more mechanical advantage because it's going to split down into whatever you're cutting up, right? It's going to do it easier, chop up the zucchini faster or whatever you're doing. And if you've got a thicker one, it's going to require a lot more force, right, to get that knife through whatever it is you're trying to cut. So your thinner wedges, you can think of them as sharper, right? In some cases, especially if you're using tools, right? Like kitchen tools. You can think of it as being a thinner one is sharper.
Well, if the thin one is easy to like cut things with, then how come it's easier to cut like cucumbers with a knife instead of paper?
Well, that would be because of the rigidity of the knife versus the rigidity of the paper. So your paper, again, so you're dealing with force and net force overall. So I'm putting in the force, right? And if I've got my hand on top of a blade, I'm putting in the force, and whatever tool I'm using between me and whatever I'm acting on, say my cucumber, then my force can't crush that paper, right? I mean, if it crushes the paper, it's not going to cut. You can take certain, like there are under certain conditions, they've actually managed to make sort of that kind of thing work. And it has to do it has to be moving. Like, this is how you get a paper cut. All right,
Oh,
like
yeah,
you can push your hand against the paper all day and it's not gonna hurt you because of the force you're putting on it is causing, your force is greater, so your net force is positive and you're crushing whatever that is. But if you've got a piece of paper and either your hand moves around it or the paper moves, you get a cut, right?
People have made saw blades out of paper, but
Yeah.
it can't be just one piece of paper, because otherwise it's too flimsy,
Mm-hmm,
so you need to do multiple.
yeah,
Like, they even tested like construction paper, like the
Mhm.
craft paper.
Yeah.
Paper,
mm-hmm.
I don't remember which one was better.
Yeah, it has to be pretty rigid. And if you have it moving fast, I mean, water can be used to cut things.
Yeah.
Have you ever actually watched them peel the asphalt off a road they're about to repave? They do it with water. Because they did it in my first house, they did it on the neighborhood street, and Cole was like 2 years old, and we went and sat in the front yard and watched it, because I'd never seen it up that close. It was like right in front of the house. And the machine that they drag along has like 12 jets under it that are aimed at the pavement, and it's water that cuts the asphalt up. So it's super high pressure. It's like, if you've ever pressure washed, anybody ever pressure washed, it's so satisfying. It's hard work,
It is
but it's very
really
satisfying when you're doing this. The driveway's getting clean,
And
right?
you get little pieces of wood thrown at your face.
Ow, that's no fun.
Yeah.
Yeah.
I learned the hard way.
But a pressure washer, if you accidentally run it across your foot and you're not wearing good shoes,
Bye-bye toes.
it can cut depending on how strong it is, or it can really hurt. Yeah, it's just water, right? So I mean, if anything that if it's given enough force, it changes that whole equation, as far as where that force is acting and how that force is acting. So that's actually a really good question. All right, so mechanical advantage of a wedge is given by the ratio of the length of its slope to its width. So what's the mechanical advantage of a wedge with a thickness of 8 centimeters and a slope the length of 104 centimeters? What do we think? I'll give you a minute. All right, Xander, what you got?
23.
23. Anybody got anything different? Lucas? 96. Colin? 13. All right. Last one, Yusuf.
13, I got
You got 13 too. All right, so W sub L, length of your wedge, W sub T, the thickness of your wedge. Oh, that's so hard to remember all these. W sub L, R sub L. It's right. Spells it out, right? All right. So here's your IMA. You have 104 centimeters divided by 8 centimeters. You're going to get 13. All right. So your mechanical advantage here is 13. 13 what? 13 nothing, right? Just 13. No units. That's so counterintuitive in science. You always expect there to be a unit. So it's kind of weird when you're doing mechanical advantage and you got no units. All right. Inclined plane, screws. Okay. A screw is an inclined plane, but what's it wrapped around? Milo? Yeah, it's an inclined plane wrapped around a cylinder. Okay. Now, if you're going to determine the mechanical advantage of a screw, I hope you like lots of math and you're going to do like tons of little calculations and work it all out. Because step 1, you got to determine the circumference of the screw head, the head. Okay. Then you got to figure out the linear distance the screw would go around if twisted 1 time. The linear distance, so basically how deep into the wood or whatever.
We're not doing this in the midterm, right?
No. Basically, like how far, if I turn this wood screw once, how far does it go into the wood? That can be determined by the width in the threads, which is called the pitch. So if you look at a screw, the threads have a pitch. If you look at a bolt compared to a wood screw, for example, so like picture your standard kind of, run into Home Depot, any bolt. Are the threads closer together or further apart in a bolt versus a wood screw? Jane? Closer together in a bolt, and in a wood screw, they're further apart. So if you're turning a bolt once around, you have to turn it a lot around to get it to go down into whatever you're actually tapping it into, right? Versus if you have a wood screw, you turn it much fewer times because the threads are spread apart. Also, a wood screw has something else going for it as compared to just like a bolt. And it's, what were you gonna say?
It has the pointy tip.
It has a pointy
And
tip.
Still.
And yeah, so exactly. So it has it has a pointy tip because you can actually take a wood screw if your wood isn't too hard and your screw's not like too wide. You can actually take a wood screw and you can take a little hammer and tap it like a nail till you get it just standing up in the wood, and then you can just start turning, right? Without even like drilling a pilot hole. Sometimes you can do this. If you have too thick of a screw or your wood's not spongy enough, it's going to split. So pilot holes are always a good idea. But if you look at the threads next time you're using a wood screw, not only does it have the pointy end, but the actual threads are like a little wedge too that wrap around it. So it's like an inclined plane going this way with a wedge going this way so that it cuts into the wood as you turn, right? And it cuts all the way down into it. You can't do that with a bolt. Like you can't turn a bolt into a solid piece of wood without drilling a hole.
The rat has what looks like a sewing machine, but there's no cloth on it.
Yeah, it's some kind of a vise because if you look here, he's pressing this piece down and you've got some kind of a screw.
It could be like a screw drill bit, like the
Mhm.
screws, like. 'Cause
Could be something like that.
That's what they used to do to screw a hole in metal.
Yeah.
They would like rotate the like crank.
Yeah. Uh-huh. Mhm.
What do they make in the factory?
I would love to know.
But
I mean, Dolly had some very interesting ideas of what simple machines basically looked like, because I'm like using something with a screw and it's like giving me things that aren't quite real things. Like everybody's trying to figure out what the heck this piece of equipment is for. We can all just
I
imagine.
think we have one in our house that's like that.
Oh yeah, there you go.
That's actually just a drill.
It looks like it looks like a drill press, or maybe a like a vise or a
Yeah.
like a printing press has that big thing and you crank it
Oh,
down with the
yeah.
vise, right? So a vise has a screw in it, right? If you've ever used a vise, it has a big screw. Yeah. All right, so you determine the linear distance that the screw is going to go down into the wood or whatever you're doing if you twist it one time. And then you have to divide the circumference of the screw head by the pitch in between the threads on the screw to calculate the mechanical advantage. So screws with threads that are closer together have a greater ideal mechanical advantage. So you may have to turn them more times, but they're doing a lot of work because their threads are very, very close together. So they're making their way into whatever it is you're trying to tap them into. Anybody ever had a bolt break off in something? Yeah. Do you know how you get it out?
You don't.
You weld something to the end and then twist.
That's one way to do it. One way to do it is you weld a piece of metal to the end of the bolt, and then you take whatever you've welded and you use that to turn the bolt back out.
Or you drill a hole in that and then start it as a screw.
Yeah, so there's something called a tapping bolt. So this actually, we have experience with this, unfortunately. So on my Mustang, 2 years ago, we had to change out, first we changed out the oil pan because it just had like a little bend where it has like a bolt that's the plug for the oil. And it was like it was a little bent after being around for 50 some odd years. So it didn't seal well, so it dripped. So we replaced the oil pan. Cole and I did it. We were out there till 2 a.m. under the car. This was the time I actually laid my ponytail in an entire tray of motor oil because I didn't realize it was in it. Yeah. And both Cole and Michael Boster said nothing to me until I stood up and it was just dripping. And I was like, did no one notice? So after that, it was no more ponytails. It was bun only. And I had to put dish soap through my hair like 4 times. And if you want to know what dish soap in long hair feels like, it's like straw. But anyway, I digress. So
did they notice?
We had changed. No, not until I was like coming in the house, like, and you know, my dad's a mechanic, right? So I called him and I was like, guess what? I did something under a car today that you've never done. And he's like, oh, what? Like, and I was like, oh, dude, I soaked my entire ponytail, whipped the oil all the way to my scalp. He was like, oh, no, I've never done that because he didn't have me here. But say none now. He just shaves what Lil has. So anyway, we replaced that oil pan. So we knew it came off nice and easy. What they were trying to replace is distributor cap on the top of the engine, right? So there's like a shaft that goes down and it kind of goes in a place where if it's not quite set, the shaft will fall off the distributor cap and down into the engine, which is not great because you have to get it back out. You can't really leave it in the down into the oil pan. It's like sitting in the oil pan. So we tried to use an endoscopic camera and pull it out. They finally gave up. They took the oil pan. And as they were tightening the bolts back on, there was this bang. And Michael goes, oh God. And I'm like, what happened? I broke the bolt off. Now the oil pan that had been on there 50 some odd years. This one only been there like 3-4 months, already broken. So we have a friend who's an airline mechanic, works down at Delta Tech Ops. He has all the tools. So we called him and we're like, hi, can you come out here? We'll pay you. He refused to let us pay him, but he has a tapping bolt. And we could have bought one and we would have, but we've never done it before. And if you mess up an engine block, you've messed up your engine block, like you're done, right? So what he did is this tapping bolt. So say this is you're looking at the part of the bolt that you snapped off. It's like right here. So the tapping bolt has like a really, really strong metal alloy that can drill into the metal that the bolt is made of. So it's even stronger than whatever the bolt's made of. And it drills down into it. And then it's like, because it's so wide in there, when you back it out, it takes the bolt with it. So he did it because it was right in the center and he's done it 100 times. So he was in and out from under my car in 30 seconds, where we would have been terrified of destroying a, vintage engine block. But so there are ways to get bolts out when they break. So yes, good mechanical advantage, great tool, really scary when they snap off. Never fun.
Good mechanic and good mechanical and.
Yeah. There's also, you can use vice grips if you can grab the end of a screw sometimes and get it, but.
You have to make it sound like in the item though.
Yeah.
If it's in the thing, you're getting screwed.
Yeah, you're kind of stuck. All right, what's this one gonna be for me, Lucas? Pulleys. Okay, pulleys fit into a groove in a wheel, but it doesn't have to be a wheel. But they change the size or direction of your force. All right, so we just size and direction. We're on your lab, right? One of your questions was about if it doesn't change the size of a force, it changes the direction. So you don't have to have a wheel, because you could toss a rope over a tree branch and now you have a pulley, right? People have done that many, many times. People do that when they go camping, right? Put their food up in it so the bears don't get it. You've seen people do that? Get it up out of the way. All right, so your ideal mechanical advantage of a pulley is actually going to be the easiest of all to calculate. All right, so it's equal to the number of rope sections being supporting the load being lifted. So your amount of force required to lift the weight with the pulley is equal to half the actual weight. So that means a single pulley can provide a 2-to-1 mechanical advantage. So you do work over twice the distance, but you're putting in half the force. So this makes perfect sense, right? If you have a rock at the end of a rope and you're pulling it up, this is the distance, and you're using exactly the amount of force you need to lift the rock. You add a pivot, and now you're gonna pull down, right? You've changed the direction, but you have 2 sections of rope that are the same length. So now what you've basically done is you've divided the amount of force you need in half because you've doubled the length. So it's a 2-to-1.
But if you do it on a tree branch, the tree branch isn't gonna move, now you have a lot of friction there.
This is true. So out there, I don't know if y'all have noticed, but I have a chandelier that's kind of hanging in the middle of the yard. So when we have parties that have outdoor stuff, like we use the fire pit, I lower it and I put little LED candles in it. It's really kind of nice. Oh, pretty. But it's basically that branch that it's hanging from is my pulley. So I have to, if you get it started, it's not too bad. I kind of have to do like I'm ringing a bell, get it moving, and then I can lift it up and lift it down. But you have to break through that kind of initial friction. And yeah, if you had too much friction, sooner or later, you'd catch the tree on fire, which wouldn't be fun. You'd have to have a lot of friction for that though. So the way we do this with pulleys is super easy. It's called counting the lines. It couldn't be easier than anything. It's easy. So you calculate your mechanical advantage by counting the lines, which are basically your rope segments. So this is what it's meant. 1, 2, 3. What's your mechanical advantage? Well, it's a 3-to-1, which is 3, right? 3 divided by 1 is 3. So super easy. And it makes perfect sense. Because like I said, if you're lifting from here, you have no pulley, this is your length, right? And that's also the same amount of force. You add more length to it. This one's not quite exact because it's a little shorter, but basically you've cut the amount of force you need in half because you've doubled the length. So it's as simple as counting the lines. Types of pulleys. Okay. Which kind of pulley changes only the direction of the input force? Ridley. This is a fixed pulley. Okay. Did you make a fixed pulley in lab today?
Yes.
Yes. All right. How'd you do that? What'd you do, Bailey?
We attached it to the ring on the top and then pulled it over. Not like pull the string over the pulling out the ring.
Super easy. So my rope out there, when I pull my little chandelier up and down, it's pretty much a fixed pulley, right? I'm not moving my tree branch. Tree branch stays the same. So here's your fixed pulley. It doesn't move. The rope moves and the mast moves. All right. So, oh, you have a question? You want to answer the next one? Okay. So what kind of pulley changes direction and size? of your input force. Oh, wow. Okay, Drew? This is your movable pulley. All right, so this is your one that looks like this. Did you make a movable pulley today?
Yes.
Okay, how'd you do that? What'd you do? Lucas, what'd you do?
Honestly, not that.
Oh.
I'm just wondering how Ozzy is napping with that thing toweling over him.
He didn't care. How'd you do it? How'd you build it?
We hung the pulley and then pulled the rope.
Hung the pulley kind of in the middle and pulled the rope, right? Okay, so yeah, so it looks like so, right? You can have your pulley down at the bottom and you raise up and it comes up as opposed to you pulling down and it goes up, right? Makes sense, all right? Then you get, what's this one gonna be? Okay, Liam? Pulley systems, all right, so these are any kind of compound pulley situation. So that's like this guy here, which is a compound. And this one right here is a block and tackle. Well, block and tackle or all you did one today, didn't you? When they're block and tackle?
Yeah.
Yeah, there is. You see these a lot on ships. You know, they're something that sailors and fishermen are very used to is our block and tackle. All right, so if you're gonna find the mechanical advantage of a pulley system, basically what you have to do is you have to isolate each pulley within the system and determine its mechanical advantage, and then you kind of put them all together. So you isolate your simple systems within your compound systems, you count the lines, and then you end up with this, determine the mechanical advantage of one individual simple system, and then the multiple mechanical advantage of the individual systems come together, get your overall mechanical advantage, right? Uh-oh. All right, now, before I show you these, we're gonna take a few minutes. My friend here borrowed my cardigan earlier today. It was hot. So, all right, somebody find me a simple machine. What do we say? James, come here. Come here. Yeah, come here. Get your butt up here. Come here. Nah, yeah, I can't move. I'm stuck and frozen. Okay. So what machine are we looking at with an elbow here? You wiggle it around. Okay, where do you think the effort is? Where's the fulcrum? Where's the effort? Where's the output? Okay. Right, so where's your fulcrum for sure? That's the easiest one. Yeah, your fulcrum's gonna be at your joint and you've got a muscle. So if your muscle is gonna be lifting your elbow this way, so you're doing this, right? He's like, give me money. I want to be paid. So if you, okay, so you lift his elbow up like this. So if this is what's happening, where do the muscle attachments have to be, you suppose? One up here, right? And one down here. So as that muscle is contracting, where is it putting, where is the effort going? On this lever from here to here. Yeah, so we've got effort going down here and then your pivot here, right? All right. All right, I won't torture you anymore.
Okay.
Somebody find me a different one. All right, Bailey, what you got?
The knee, I guess the lower.
He's about to lose his leg. All right. All right, let me see here. You can see, everybody can see it better if I do like so. All right, yeah. Okay, what you got here now?
Just a leg.
Mm-hmm. So we got another lever, right? So but this lever goes this way, right?
Yeah,
So,
there's the fulcrum.
right.
And then usually it's your tendon. The tendon goes all the way from to lift like this. It's
Yeah.
Back you all the way up your leg.
Yeah, which tendon is this?
Your Achilles tendon.
Yeah, if you're doing, yeah, okay. So what are the differences between tendons and ligaments? Do you know? Do you remember?
One snap, you're screwed.
Yeah, ligaments snap, you're screwed. Do you know, Drew?
Ligaments attach bone to bone, while tendons will attach muscle.
Spot on. Ligaments do bone to bone. Tendons do muscle to bone. All right, excellent. So, yeah, there you go. You can hold it. It's heavier than you think it's going to be. Yeah, it's just like,
A leg now.
she has a leg. Anybody else see another machine that's part of this? What do you see?
The skull.
The skull. Okay, what do we see in the skull? I'm very curious. What do we see in the skull?
It's like a Class 11, so this is a full time.
Ah, the jaw. All right, let me try to see you guys see. Not the jaw. Oh, right here. Okay, do you know what these top vertebrae are called, by the way?
Brainstem.
Brainstem.
That's the bottom of your brain, yeah. So actually, these top vertebrae right here. So, gotta look close. So if you look at the top vertebrae, you've got these top two are different than the rest. Basically, you have what's called an atlas and an axis. So you can say if you want. So who's atlas? What do you do?
He. What is the name? Human spire.
Yeah.
I know.
Oh, Prometheus, yes.
He's the one that carries the water on his back.
Yes, Atlas, have you ever seen like statues or art depictions of Atlas? He's got the whole world like this, right? So your atlas is the vertebrae that holds up your head. Perfect name, right? And then the axis is the one that does all this stuff underneath. It allows for the pivoting. All right, does anybody else see a different machine? What's a different machine? What do you see?
But all the joints are full.
The joints are not bullets. What are they? They're levers. Most of the joints are similar to levers. Some are similar to something else. Anybody see something else? In a joint, maybe? Close, real close? Colin? Fingers, yeah, fingers. What do you see, Kate? What does your ankle do that's different? What do we see in an ankle? You got a lever there for sure. Ah, and your ankle can do some rolling, right? So that's telling you something. Where else can you roll within a joint? Drew.
Your hip muscle.
Your hip. Okay, look at this. Does this look similar to something?
Wheel and axle.
Ah, it's not quite a full wheel and axle, but it's real.
It's a ball and
similar.
socket.
It's a ball and socket. Yeah, but it's
Well,
very
it's not the ball, the other is the socket.
Yeah, this is the ball.
Like-
This is the socket, and it behaves similarly to a wheel and axle. Not like full on, yeah, definite wheel and axle, but very similar. What else? What do you think, James?
You can't see it, but there is a protein that is a screw.
Oh, yeah. Mm-hmm. Yeah. And your muscles all function like ratchets, which are basically like little tiny incline planes that lock, right?
Mhm.
All your muscle fibers behave exactly as a ratchet behaves. What is that back there? That's noisy. All right, we've seen, so we've got some levers and a potential wheel and axle. What are other machines? Lever, wheel, axle, screw, inclined plane, wedge, and pulley. So do we see any of these? Anything else? I see wedges. Bingo, James, teeth. Yeah. Especially your incisors, right? Okay, so people can do what they want with their lives, but if you look at a human's teeth, we're meant to be omnivorous. Evolved to be omnivorous because we've got grinders back here. I'll just turn it back in, right?
That's
So
why an overbite.
you got your grip, yeah. All these back molars are for grinding, right? And all these front teeth are for tearing and cutting. So if you look at a horse's mouth,
They have all sorts of brains.
yeah, they have, say it again, Bill, when they got.
They have some molars, like, except they're not molars, they're all terminals.
Yeah, so if you look at a horse, which is an herbivore, they don't have quite the setup of incisors we have, right? They have giant molars. Horses' teeth are big. And animals that are meant to like do a lot of grinding, usually herbivores.
Cows.
Yep. A lot of them have teeth that don't stop growing.
Oh, rabbits.
Rabbits, hamsters, beavers, right? They have these teeth that just grow, right?
Hey, Rat.
Yes. There are, yeah, there actually, there's some cows whose horns go around and poke into their cheeks and stuff too, and that's no good. But yeah, with teeth, there's actually a little squirrel. She's got an Instagram and a Facebook. Her name Thumbelina, little Thumbelina girl. You ever seen her? But she was rescued as like a little pinky, like a little naked thing, you know, a little hairless thing. But anyway, she lives in these people's house like a dog. It's really weird. Like she has a little crate that she goes in, but she just runs around. They have a whole Instagram channel of her. But she had to have surgery because one of her teeth was like, they grow and she doesn't live in the wild. So, and one of her teeth came poking out.
Some people actually grow up into their skull.
Mm-hmm. Yeah.
Yeah. And it will kill you because it will damage your brain.
Yeah, that's not good. Yeah, if you've got teeth that are misplaced like that. Uh-huh.
Had teeth behind where they're supposed to.
Yeah. Mm-hmm.
Like,
That happens a lot. Like I have a friend who her son, his teeth he had teeth that never grew, like his second incisors never grew. So he's either gonna have to get implants or they're gonna reshape his canines to look like incisors. So what were you gonna say?
My mom's family has a history of missing teeth,
Mm-hmm.
especially canines.
Ah,
This
Yep.
one's missing teeth.
oh, no canines for you either? Yep.
It's a genetic thing. One canine and 2 bones. Mom's missing one. It's not.
So there's actually a really interesting, there's a YouTube channel, and I'm pretty sure he has it on Instagram too, but he's a guy who does, I can't remember his name or I would tell you. He's a guy who does horse dentistry, which apparently can be, for horse owners, a very big deal. Because in the past, they would typically take these horses, they would have to put them under. So you'd have to take them somewhere, have them put under, they'd do all this stuff. It was a big deal. But this guy's found ways to like do conscious sedation and whatnot. And I watched this guy like go in and take the horses just standing up, you know how they do, but they like put a sling around it so it kind of holds its weight a little, and they just gave it a nerve block like they do to you when you go to the dentist. And somehow this horse was chill enough. This dude had like equipment in his mouth and was pulling out teeth because he had like a big old tooth like this that was all like abscessed and messed up. So yeah, teeth are wedges for the most part, at least the front ones are. Another weird, if you like weird YouTube channels, I'll tell you one that, okay, let's all admit it. Who likes Dr. Pimple Popper? Okay, a lot of people do. A lot of people will watch the videos where they're like draining cysts and whatever, because there's something weird in the human psyche. So better than that is there's a guy, especially if you're interested in animal care. So there's a guy, there's an American guy, I can't remember the name of his channel, but there's a Scottish guy, his channel is the Hoof GP. And I didn't realize this because I know what farriers are. Like farriers fix horse hooves, right? They put shoes on them, they trim them. Well, apparently cows have the same problems, which I never really thought about. But cows' feet need to be tended, and sometimes they will step on things, like out in the corral, they'll find a nail, and that nail will go up into their foot, and then they get lame, and you don't want to put down a perfectly healthy cow because her foot's infected. So this guy, they have this thing, it's called a crush, scary sounding thing, but it's this apparatus. Yeah, they walk the cow into it, and it basically like locks around the cow and it kind of lifts the cow up. And while she's in there, they like tie a rope around their leg and it'll lift the whole foot up, and it puts the whole foot like this right in front of the guy. And he can work on the foot, and he'll shave it down, and he'll get like a sander and really buffs it down. But it's really interesting because all of that has to do with like the way the bones are situated, the way the hoof grows. It's all aligned to give the best advantage to the cow. So when something gets out of whack, obviously it causes that cow problem. So anyway, if you want weirdness, one more interesting thing. So these are technically joints up here, but we call these sutures. They're technically joints because it's where two bones come together. In an adult human, or even somebody aged, mature human, they are closed. They're called sutures because they look like it's been stitched. What are they from? Okay, PJ.
Wait,
These up here.
that soft spot in your head?
Yeah, that would be up here. That's your fontanelle. It would be right about there-ish or here-ish. There's one back here too. What else?
For when the baby's born.
Yeah, and have you ever seen a video of like a cow or a horse or a dog or a cat or anything like that being born?
No.
Yeah, you ever seen them? It's pretty cool. They just slide right out. Mom just walks off. dragging them behind them or whatever they're doing. But if you look at the proportion of say a kitten, look at the proportion of the kitten's head to its body.
Sounds bigger.
Yeah, it's bigger, but in a kitten, it's not so much bigger compared to humans. If you look at a baby's head in comparison to its body, it's like a third of its body, right? Like a newborn baby, like a head is about a third of its length. That's a lot. Why are our heads so darn big? Like, why are our heads so huge?
We still have to have a brain.
That's like, yeah. All right. So this little dude here now on the floor. Sorry, friend.
She's trying to hide.
Come here for a second. I'm borrowing you. You have to be very careful. All right. So his head's about the size of a good Honeycrisp apple. All right. How big do you suppose his brain is in there?
It's very small, he's not as smart as dog.
Aw, you're dumb. Probably like a grape. Yeah.
That's bigger than a grape.
Maybe a tangerine on a real good day. Probably like a walnut's probably a good, yeah. Somewhere in between. Right?
Planet.
Aw. How big is your brain?
Probably about the size of one of these.
Yeah, you think?
One of these.
Yeah, your brain's considerably bigger. Uh-huh.
Your brain is the size of your two fists put together.
Yeah, that's a good way to do it. Yeah, roughly. So our brains are much, much bigger. Because our brains are bigger, our heads are bigger. But we would all kill our mothers if we didn't have a way for our heads to collapse on the way out. Collapse, which is why all of these bones are not connected when you're born. There's also multiple bones here that don't exist when you're born. Yeah.
Kneecaps.
Yeah. Next time you're around a baby, check out, a baby, not a toddler, a baby. Check out their knees. We don't have kneecaps yet. So that's because a lot of places, there's cartilage that will ossify, right? It'll turn to bone, but it doesn't start out that way. So there's good old Wilhelm. Thank you, Wilhelm, for the tour.
You went to like several times.
And I don't know if any of y'all follow, but I posted to our Instagram and our Facebook. Last week, I found something I'd never seen before. Don't know how I missed it, but it is an X-ray of Nikola Tesla's foot.
What?
Yeah.
Who?
Nikola Tesla, who was like one of the coolest scientists ever. Anyway, he actually invented and was working on the X-ray machine at the same time as Wilhelm Röntgen, who gets the credit for it. But there's an X-ray out there. There's actually one also of his hand, but it's not as widely publicized. But there's one of his foot, but he did it with his shoe on. And you can see all the nails in the heel of his shoe and all the metal pieces in his shoe. Because it was in the 1800s. Yeah, you can see all of it. It's really cool.
The bone of your foot looks really weird.
Yeah, foot bones are, well, they do look weird. All right, so I have 2 Rube Goldbergs to show you today. This is the first. This is inspiration. All 6 simple machines are here. Now, you guys aren't going to be required to give me all 6, I don't think.
Well, last year.
But, or maybe we are. Maybe we're all 6. But
Thanks.
I can't remember. But anyway, this is pretty good. So let's see. See if you can watch them all here. Because some of these are pretty cool. Good. Yeah. Then I gotta pause it for a second because you don't want it jumping. Too much is going on for it to be glitching. There you go. This one is so complex, but it's so cool. Yeah, it kind of shows you back from the beginning. It's just got different angles, but yeah.
Oh, yeah.
I mean, pretty cool. Going on, moving on. So they speed it up, they slow it down. It's pretty cool. So if you take all those simple machines and you put them together, you've created a compound machine. So anytime you put more than one simple machine together, even if it's just two, it's still compound, and they can get more and more complex. So gears, that's an example of where you've got one wheel and axle linked to another wheel and axle, and then the teeth are used to lock them in place, right? All right, so you're going to build a compound machine. Now, that's what your Rube Goldberg project is going to be. And I am going to try to get all that information together, like I said, before you leave for Christmas. So, what do you not know? Final project?
Yeah, he did.
Yeah.
Final project.
Oh, final project, you're going to build a Rube Goldberg. You're going to be outside, so you can take advantage of like the pitch of the hill, trees, everything. It's going to be fun. All right, this is the last one. I'm going to let y'all out a little early today because it's Thanksgiving. But this is a 70-step basketball trick shot, which if you've ever built a Rube Goldberg machine, like that last one is crazy impressive because even if you put 2 or 3 simple machines together and you're trying to accomplish a goal, it can take you days of triggering and resetting and triggering and just trying to find all the little perfect positions and angles, and it gets crazy. So I don't know how long this took this person, but I'm very impressed. So this one's really cool. Mm-hmm.
Oh, who's that first one there?
Yeah, I can't even do that part.
I actually got a perfect run and they didn't record it.
Oh god, yeah. Yeah, this guy's taking advantage of the entire property here.
Maybe someone had to call it project.
Yeah, that's impressive. Yeah. Mm-hmm.
I have a feeling this was either some kind of thing that they were
I
supposed to
think-
do for school, or this was during COVID.
I think it was COVID. Yeah. Mm-hmm. Look at that. That's very smart. Look at that. This is wild too. Look at this. How pretty is that? Look at that. It's even pretty. Love it. No, I think he's walking around with the camera in his hand.
If they went like
often, like, whenever
Yeah,
I
I
buy
know,
them,
too.
Look at this.
Drones would mess with it with the air.
Yeah, you have to be real careful with them.
they went.
Look at that. Whoop. It's a long way.
Big property.
Mm-hmm.
Imagine just.
Oh.
Because it could be on a tripod.
Your arms exist. You're a tall guy.
Here's the basketball.
Yeah, we finally found the ball. But wait till you check out this incline plane. This is a little nuts. Clearly, he dug it. Look. This dude was for real. He was not playing around. Look at this. Watch this. It's like, look at this. And ta-da! I mean, come on. Right? Yeah, they take a long time. So, okay, before you run out, so, don't show up next week. Everybody knows that, right? I won't let you in. If anybody has any questions about anything, let me know. I am gonna put on, y'all, hold on. As you're leaving, because some of you have to wait for rides or whatever, I am gonna put on a video of 4 years ago, the last classes run with, oh yeah, okay, with all of the Rube Goldberg machines that they did, which
Mine's
were
the best.
pretty cool. Yeah,
Completely.
they were fun. They were a lot of fun. So I have to get this out of the way and we'll be good. Yes. Yes.
I use butter.
When are they? They're the 15th or it's that last, just whatever that 14, 15, what's the date? Hang on, I'll tell you. It's the 12. Mhm.
December.
Yes.
December
Mhm.